Okay, previously we looked at this very simple shift register made out of D flip-flops. And just to summarize, we found that because of the set and reset functions, or the reset and the set lines, we were able to force a 1 into the first uh, flip-flop. And then what happens, because the flip-flops are connected, Q to D, Q to D, Q to D, and then wrap back around. This is what gives us the ring, Q to D. That the 1 basically transitions from one flip-flop to the next flip-flop, and it looks something like this. And then when it gets to Q4, the next clock, rising edge of the clock, it goes up here, and then it continues down here. So we can make something that's a very, very simple counter. So what we're going to do is, and it's simple in the sense that there's no other circuits that we need. It's just hooking up a bunch of D flip-flops. And so what we're going to do is we're going to take a look at this and make a little bit more complicated counter. This is a more complicated counter because it has three flip-flops. And you say, well, that sounds easier, okay? But it counts in a different way. So here's what we're going to assume. If we and there are three outputs: bit Q0, bit Q1, and bit Q2. So if we list them up here, this is Q2, Q1, Q0. So here would be Q2, Q1, Q0. Let's say we start at 0, 0. Okay, and that starts at 0, 0 because we're going to reset it with this switch, and the resets are hooked. This switch is hooked to all the resets. So we're going to start at 0, 0, and then when the clock comes, the rising edge of the clock, and where's the rising edge of the clock? The clock is right here, coming off of here. When we have the rising edge of the clock, we want it now to go into Q2 is equal to 0, Q1 is equal to 0, and Q0 is equal to 1. The next clock cycle, we want Q2 to equal 0, Q1 is equal to 1, Q0 to equal 0, and then etc. So we're going to count in this direction. After we have them all set to 1s, then we're going to repeat it by forcing them back to 0, and just repeat that cycle. So this is the same state as this over here, the initial state. Now, what is this thing? Well, if we look at this representing a binary number, this is 0, this is 1, this is 2, 3, 4, 5, 6, 7. And then we reset to 0. So this is called a 3-bit because there's 3 flip-flops in it. Binary because these are binary numbers up here, and it's a counter. Why is it a counter? Because it counts from one binary state to the next, to the next, to the next. So it's counting along. Okay. Now, in general, I don't know how to hook this thing up. Okay. Try as I may. I don't see any nice way of hooking it up. So here's what I'm going to do. I'm going to suggest that the next state for this first flip-flop is going to be determined by some kind of a logic circuit. And the logic circuit may have a bunch of things going into it. I believe the only thing the logic circuit has to have, in this case, it has to have the value of Q0, Q1, and Q2. So what it says is, based on the current state, this current count, what would be the appropriate 0 or 1 or the appropriate D input to cause this counter to go to the next state. So let's take a look at this real quick. Let's say that we're sitting over here at 0. Okay, so we're in current state. Here's our current state. Okay, so in this case we have Q0 is 0, Q2 is 0, Q1 is 1, and Q0 is 0. What do we want the D to go to over this? So what is this supposed to be? So we go to this state. Well, if we want it to be 1 because the next state is 1. So we want this magic box called the next state for Q0 on the basis of having a 0, 1, 0 to produce a D be equal to 1. Okay, so what we need to do is we need to come up with what is in this box, what is in this box, and what is in this box. And what these boxes are called, they're called state transitions, okay, in the general. So we need to find out what is the outputs of these next state functions. So we're going to go after those, and it's going to take a little bit of logic design to do it. So this is what we had before. This is the count that we're dealing with. It's going in this direction, okay? And then this is actually tells us what the next states want to be. So when we're in 0, 0, 0, the next state we want to go into is 0, 0, 1. And so that means that the next state that we're going into means that we want this point, which is next state 2, to stay as a 0. We want next state 1 to stay as a 0, but we want next state 0, which would be this value for the D, to go to 1. Okay, so let's go through and let's suppose we're in current state 0, 0, 1. What do we want the next state to be? Is 0, 1, 1 or 0, 1, 0, and then so on. So what we're going to do is we're going to use these outputs and apply these signals to the D flip-flop, to each D flip-flop, so that it will cause this counter to count to the next state. And this is a general example of a state machine. So let's see, let's take one that's easy and let's try it. Okay, the main thing now here is designing the digital logic that makes this happen. So let's see, here is the example we had, and we're just going to look at next state 0. So we're going to look at this column. Okay, so how do we generate next state 0? Okay, so we find that next state 0 is 0 here, 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 here. And the only time it's 1 is when we have all the states are 0, or the states are 2, or the state is 4, or the state is 6. Okay, so what we do is we list this. This is the time when next state 0 must be 1, when next state 0 must be 1, next state 0 must be 1, next state 0 must be 1. So since it's on this one or this one or this one, we can write this table in this form. Okay, so what's happening here? We use this term and we apply it right here. We use this term and we OR it to the previous term. And then we use this term and we OR it to the previous term. And then finally, we use this term and we add it to all. So this is the Boolean equation for when is next state 0 to be 1. Okay, so let's see if we can simplify that now. Okay, well, first of all, note that all of the terms have a not Q naught. Is that true? Do you see it right here? Okay, all of them have a not Q naught. So just as we can do in regular algebra, we can factor the not Q0 out. So convince yourself that this is the same as this. Okay, we just factored it out. Now, let's take a look at what this particular piece is. Okay, well, this piece is always 1 because there's no value of Q1 and Q2 that will not make this 1 because this is all possible values of Q1 and Q2. So if this is always 1, we can replace this with a 1. And so what we find is the next state 0 is equal to 1 times Q naught bar, or not Q0, and not Q0 is just this. So what this is, the way we can actually get next state 0 is just with an inverter. We take Q, not Q0, put an inverter, and we get next state 0. I'm sorry, we put Q0 in inverter. Take this off of it. Okay, so then we get next state 0. So that's pretty easy. We can actually build that. Let's go through and take a look at a next state 1 and how we do that. We can use the same kind of logic. Okay, we look at next state 1. There we find the values that make the time where next state 1 has to be equal to 0 are right here. And that is represented by these Boolean situations. Okay, and so convince yourself that not Q2 and not Q1 and Q0, okay, here is not Q2, here's not Q1, and here's Q0, okay? That says that we want a 1 now in next state 1, okay? Convince yourself of the others. Now, we will go through and collect all these ORs, and so this one goes into here, and so on. We just collect them until finally this one is in here. And then we need to simplify those. Well, I'd like to factor that, okay? But there's no common factor if we look up here. So what we're going to do is we're going to factor it in two terms. So we're going to first look at all of the not Q2s, and we're going to factor them up into here, okay? Then we're going to OR the Q2s, and we're going to factor them into this term. Okay, this is just like standard algebra. Okay, and so what happens is then, since this term is the same as this term, we can simply rewrite that, and we can rewrite this as Q2 plus not Q2 plus Q2 times this thing. Okay, but let's take a look at this. What is Q2 or not Q2 or Q2? Isn't that just 1? So this thing is 1 all the time. So all we have is the next state for number 1 is not Q1, which is here, and Q0, which is here, or Q1, which is this part, and not Q0, which is this part. Okay, isn't that, we've seen this before. Okay, we've seen this piece before, and this piece before is just the exclusive OR of Q1 and Q0. And actually, we could use an exclusive OR gate in order to implement this. So this can be done with one gate that would give us next state 1. So far so good on that. Now we're going to pop off to the last one, and as you could probably imagine, the last one's going to be a little more complicated. Okay, but we do the same process. So let's go through the last one and see if we can find the process. Let's see. We're looking for all places where next state 2 is equal to 1. That will cause that flip-flop, the Q3 flip-flop to go to 1. Okay, from these states. And so what we do is we look at next state 0 is equal to not Q2, which is here, Q1, which is here, and Q0, which is here. Okay, so we look at these 4 terms and we write the 4 terms along here. Okay, now what we can do is we can factor these terms also. Okay, and the factorization becomes a little harder. So what we do is that this term becomes this, and then these 3 terms become this. Okay, so it looks like we got kind of a big mess. But there's something interesting here when we're dealing with this. Let's focus on this piece. Whoop. I don't know what that was. Sorry about that, guys. Okay, let's focus on this piece over here, this underlined in red. Isn't that basically all the values, okay? This is all the possible combinations of Q1 and Q0, okay? Except Q1 and Q0 both being 1. So the only thing that we don't have here, excuse me, let's get this up, is we're missing the plus Q1 and Q0. That's what we're missing, okay? So this is everything but. We can write this, and I'd like you to try it, write the truth table, is that all this red stuff becomes just Q1 and Q0 not with a not over it, okay? So now we can simplify it quite a bit into this form, okay? So let's go through and see if we can actually design a circuit that would perform that function. So the first thing we're going to do, and this is the terms that we've been dealing with. This is what we had previously. Okay. So what I'd like to do is to go from NS1 and work backwards. Okay. So in order to get, I'm sorry, NS2, there should be an NS2 and work backwards. So what we find at NS2 is equal to this term or this term. And where did the OR come from? The OR is going to be this OR gate here. Okay, so we have that. Now, we don't know how to get these terms yet. So what we're going to do is we're going to take one step further, and the one step further is going to be this. So in order to make Q2 and Q0 and Q1 not, what we're going to do is we're going to use an AND gate, and we're going to present Q2 to it, which is this Q2, and then we're going to present this to it. Okay, so convince yourself that that gives us that term. How do you get this term? You do the same thing and you do it down here. Okay, that gives us this term. Well, still we don't know what these things are, so we're going to have to build these terms. By the way, these are ands and these are ors. So let's go through and build the next stage. And we're going to build the next stage, and it looks like this. So we knew what we needed at this point, okay? And in order to make, let me erase that now, in order to make this Q0 and Q1 not, what we do is we start with Q0 and Q1 and pass it through an inverter, because this is the not thing, right? Okay, well, how do we get Q0 and Q1? We just put those into an AND gate here. Okay, so we got that circuit. This brought this Q2 down already, so we don't have to do anything here. How did we get, here's a Q2 here, here's a Q2 not, so that's how we got this one. We brought that down, and guess what? How did we get this one? Well, this one is right here, and that one we already had here when we were building this piece here. So we have the whole thing. So this is actually what the circuit looks like. So let's see if we can put this circuit together. So we take the three states, we apply 2 states to this AND gate and 2 states to this NOT gate. Okay, and then we manufacture these. We pass them to 2 AND gates, and then we pass them through an OR gate into NS2. Excuse me, that's NS. There should also be NS2. Okay, so what we have is we now have a way of building that little circuit, which is kind of cool. This is the layout of the flip-flop you'll use, and you'll notice that the flip-flop is actually divided in 2 flip-flops. Here's flip-flop 1 and here's flip-flop 2, and you could use them from there. That's the end of the presentation.